Okay, so again, similar to yesterday, I'm going to kind of introduce diverging lenses, go into some of the theory, and then I'll do another video with just doing examples of diverging lenses, ray diagrams, and the math for them, okay? So this video will be about the introduction to them. Based on what you're looking for out of this, you can choose which video you want to start with or how much of each you want to watch, whatever. Okay, if you feel like you're good on the theory, go ahead and just jump to the examples. But we're going to look today at diverging lenses. Okay, so like the name suggests, it causes light to spread out, right? It makes light diverge. That's what that word means, as opposed to our converging lens where it made light come together. You can see that in play here, right? Big differences between converging and diverging. Well, it's in the name, diverging, right? So it's going to cause light to spread out. Hey, if light is getting spread out, is this lens actually going to focus light? No, how could it, right? It's making these parallel rays spread out. Well, that's by definition, that means they're never going to end up crossing each other, right? And so what can happen though is that look, after these rays have spread out, if our eye were over here, right? If we had a big eye over here, okay, we would see these rays and our brain would trace them back and we would think, huh, looks like they're all coming from this place. They're not, right? Those are not real rays that are appearing to converge there. They are virtual rays. And so this is a virtual focus, right? That is why diverging lenses you're going to see will have a negative focal length, okay? As opposed to our converging lenses that had a primary focal length because it was a real focal point. Real is positive, virtual is negative. So as these parallel rays came in, they really did meet here at the focus, the principal focus, okay? Another important difference between diverging and converging. So remember, on a converging lens, the principal focus was where parallel rays from the same side as the object would end up converging, right? Rays of light that left the object parallel to it would end up converging at the principal focus. But then rays from the other side, right, if parallel rays came in this way, they would appear to converge here at the secondary focus, okay? Now, think about that in terms of our diverging lens. How do we distinguish between the principal and the secondary focus? Well, where did these rays come from that appear to focus here? They came from the same side as the object. They appear to focus over here. They don't appear to focus over here. So rays of light that leave parallel to our object will appear to focus here. That's our principal focus. It's on the same side as the object now, whereas in our converging lens, it was on the opposite side. Okay, so principal focus and secondary focus are about where would parallel rays converge or appear to converge. That's why they're flipped for a diverging lens. So over here, right, if our object was over here, we would have parallel rays coming in, diverge out like that, and they would appear to focus there, right? And so that would actually be our secondary focus if our object was over here. So on a converging to diverging lens, I just don't want you to get it mixed up with this, the principal and the secondary focus are actually flipped. So why do diverging lenses diverge light? Let's use our knowledge of refraction and see if we can see, right? So if you can reconstruct this, it can be really helpful in your ray diagrams, right? You know how a ray should be kind of bending. So if you get a wonky result, you go, oh, whoops, I did it wrong because I wasn't thinking about refraction, okay? So ray comes in. It's at an interface between air out here and let's say glass here, right? So it's going from air to glass. That requires a normal, right? We need to think about the normal. Okay, now if it's going from air to glass, it's going to get slowed down. Glass has a higher index of refraction than air, so it's going to bend towards the normal. Again, the dotted line does not mean virtual here. Okay, this is just, I did it differently in grade 8. This just means that it's been refracted. Okay, then now what's happening? So it got bent as it entered the glass, but now it's leaving the glass. So now it's going from glass back to air. So we need a new normal, right? At an angle here because that's normal to the surface, right? And now it's going from glass to air, so it's going to get sped up. So it's going to bend away from the normal, right? So that's going to make it bend upwards even more, right? It's going to spread it out even more, just like on our converging lens where it did the opposite, right? It bent in once and then in again. Now it's bending out once and then out again, right? So that's just going to happen to all of these rays. And so that all of the rays end up diverging. They split apart. So we call concave lenses diverging lenses, much more often than we call them concave lenses, to be honest. Okay, so to show you it in real life, okay, I have here, you can see a double concave lens, a diverging lens. And so what happens as the ray of light enters the lens? Well, if it hits at the middle there, right, that's just essentially a perpendicular piece of glass, so we would expect no refraction. But as we change it so that a parallel ray is coming in at an angle, not because I'm changing how I'm holding the ray, but because the interface itself is angled differently, right? You can see it spreads out light, right? And you can notice if you trace this ray back, okay, ignore that this is the reflected ray. That's not the ray I'm talking about. That's the ray that's being reflected, okay, partial reflection. But you can see if you trace that back, that refracted ray back, it always does kind of seem to be focusing at some point, appear to be focusing at some point. It's not actually focusing at some point, of course. So it spreads rays out. And so what's that going to look like for image formation? Well, again, much like our diverging mirrors, which were convex, our diverging lens, which is concave, right, is actually only ever going to produce one type of image. Okay? It's going to produce an image that's virtual, which you might have guessed already, right? Because it will never make real rays converge. It can make fake virtual rays converge, right, that our eye perceives to exist. So it'll be virtual, diminished, and erect, which is exactly what our diverging mirror produced. So it's the exact same characteristics, okay? So as you can see why, right? As the object, as we do our three rules, the same rules we did yesterday, the object always ends up, no matter where it is, virtual, erect, and smaller, no matter where I go. So these are our three rays. I'll show you on a ray tracing diagram, again, how they kind of go, but it's actually the exact same three from yesterday. The other thing here is that the image always appears closer to the lens than the object is, right? Yes, smaller, but also closer. So what's that look like in real life? Well, I have here, it's kind of hard to tell. It's a little more subtle, the curvature, okay? But it is a double concave lens. It is a diverging lens, okay? So if I hold that over my eye, what do you notice about my eye? It's always smaller, right? No matter the distance, right? There's my face, much smaller. However, it does appear closer. So notice how my face, this image of my face kind of appears closer than it should, right? It kind of looks like, yes, it's smaller, but doesn't it kind of look like it's between me and the lens, right? It looks like it's kind of floating. There's a tiny version of my head floating there. It's a virtual image. How do I know it's virtual? Well, how did I know on the converging lens it was real? I could project it on a screen. Real rays of light could be projected with the lighter through the lens and then reappear over here on the screen. Let's see if I can do that with this thing. Right? No matter where I go, there are no real light rays that are going to get reassembled to actually produce an image, right? In fact, what you can see is a shadow of my fingers and the lens, right? And you can even actually see outside of the lens. Notice how there's kind of a blurry ring of light, right? That's due to the light rays from this getting spread out, but not put back together in a cohesive way where an image can be formed. Just these rays getting scattered out into kind of chaos, right? So there's a bright ring around the concave lens, right, where the light comes in, gets spread out. But definitely no image of the flame being produced at all. Unlike with the converging lens, where I did have an image of the flame being produced as long as I was at the right object distance, right, and the screen was the right distance away. Okay, so on page 39 of the notes here, let's take a look at how we applied, again, the same rules from yesterday. There is a little bit more thinking to do here. They're a little bit trickier, but again, there's a give and take where it's actually a little bit easier because you always know what type of image should be produced, but a little bit trickier because the rays are just a little bit weirder to think about because, of course, they're virtual rays that end up converging. So I'll hop over to paper because I think that's more useful for you. Okay, so the rules are actually the same. So any ray parallel to the principal axis will diverge from the lens, right? Okay, but a virtual ray will project back through the primary focal point. So a virtual ray will project back through the primary focal point. Again, notice here, we've switched. The primary focal point is now over here because that is where light rays from the object will appear to converge. Yesterday it was where they will actually converge, but the thing that's the same here is that it's where would parallel rays from the object converge or appear to converge, okay? So parallel ray from the object, or from the side of the object anyway, would go in parallel, hit the principal plane, and get diverged in such a way that they would get projected back through the primary focal point. So this guy gets spread out, But if our eye is over here, okay, we will see that ray and we'll think, huh, looks like it came from over here. Okay, rule one. Rule two, any ray headed to the secondary focus, so a ray that was headed to the secondary focus, will refract parallel to the principal axis. Okay, well, again, think about this in terms of a ray coming from the other side. So what would a parallel ray coming in this way do? Well, it would get diverged in such a way that it would appear to be headed through the focal point, right? So we could imagine the ray coming in like this, it would get diverged, and we know that the focal point here, right, is where parallel rays on this side would appear to converge. So all we're doing is that, but backwards, right? Geometry works that way. If it works one way, it should work the other way too. So now we're just saying, what if a ray was headed to the secondary focus? Okay, well, then it would just be living a parallel ray from this side's life, but backwards. So it would go parallel now, right? Instead of going parallel, diverge that way, projected back to the focal point, it's going projected through that focal point and then parallel on this side. So what would our eye see that's over here? It would say, huh, looks like this came that way. So all about the projections backwards with these diverging lenses. So we would see it coming from somewhere over here. Okay. Rule three, nothing changes at all here. Okay, any ray that passes through the center of the lens will come out on the other side without any refraction. Again, it gets refracted here, but then it just gets refracted here back whatever amount. So that overall, no refraction. So through the center, boom, easy enough. Okay, again, I recommend using this as one of your two and then using one of the other ones as your check. Probably rule one and rule three, and then rule two as your check, because rule two is the one that students can mix up the most often. Let's just put it all together and get an idea of the image formation. So I'll go back to my rule one diagram and I'll just do rules two and three on here as well. Okay, rule two was that any ray headed to the secondary focus will get refracted in such a way that it goes parallel to the principal axis. Because again, it's doing what that ray would do, just backwards. Which means our eye that's over here would see it come from this way. And aha, look at that. We have now two virtual rays appearing to converge. So right now we can predict that our image will be forming there. Let's go ahead and draw our third one as a check. Okay, and that looks pretty good to me. Now you might be noticing, hang on, wait, two virtual rays are converging, but then one real ray is actually there. One real ray really is there. One real ray converging does not make it a real image. Okay, you need all the rays converging to be real to make a real image, right? Only one ray is actually coming from there. These two are virtual, so good luck reconstructing an entire image of an object with just one ray. You get one little point actually projected, but that will not produce an image. One ray does not make an image. So because if any of them are virtual that are converging, this is still a virtual image. Okay, so all three rules checked out. This is definitely a virtual image forming there. Okay, just like we always should get from a diverging lens, not only is it virtual, it's erect, it's right side up, and it looks smaller, diminished. Okay, always, if you ever get anything other than that for a diverging lens, something went wrong. Notice again, it's also closer to the lens than the object is. Okay, let's get a little practice with these ray diagrams here. So use a ray diagram to predict the properties of the image when DO is less than F. Okay, well, might seem like a waste of time because we already know what it's going to be like, but the skill of drawing a ray diagram still needs to be practiced. So drawing my principal axis, principal plane, perpendicular, drawing a concave lens this time, okay? And still like before, be careful measuring out your primary focus, your secondary focus, and twice of those. So I'll go here. Okay, and just remember for a diverging lens, right, the principal focus is decided by where parallel rays from the object would converge or appear to converge. So if we're going to put our object on this side, then this, as these diverge, they're going to appear to originate from this focus, not this focus like yesterday. Okay, so this is now the principal focus. And on this side, we now have the secondary focus. Again, because I'm going to put the object on this side. If you put the object over here, then flip it again. Okay, so if DO is less than the focal length, so let's put the object, how about right in the middle? Okay, let's do our 3 rules. So rule 1, parallel to the principal axis. Oops, went a little over. Parallel to the principal axis, and then diverged in such a way that it appears to originate at the primary focal point. So actually does this, but our eye would think looks like it came from over there. Rule 2, I'm going to go do rule 3 as rule 2 because that one's harder to mess up. So we have through the center, no refraction. Okay, and already we can kind of see, okay, this is looking good because it's diverging lens, so it should appear closer to the lens than the object was, right? Good, check. It should appear smaller than the object, diminished, check. And it should be virtual, check, because we have a virtual ray and a real ray converging. But as soon as one of those converging rays is virtual, the image itself is virtual, right? Let's just do our third rule as a check. This is the trickiest one, but it's not too bad. So any ray that is headed for the secondary focus will get refracted parallel to the principal axis. But when our eye over here sees that ray, it might say, well, it will say, huh, looks like it came from back there. Okay, and great, look at that. 3, perfect, bang on. So we definitely have an image here. It's definitely virtual because virtual rays are involved in forming it. Okay. Also, quick check, anything on the same side of the lens as the object has to be virtual, right? Because real rays they're not here. Real rays from the object are going out this way. Real rays are not converging here anyway. They can't, right? They've left the object in 360 degrees. Okay, good. So, and erect, that's the other one. It's erect. Okay, what about when the object distance is equal to the focal length? Set it up here. Now, if you're saying to yourself, I bet no image is formed, I don't blame you, but we've got to think a little bit about what a focal point does, right? Okay, so think a little bit about what a focal point is, right? It's where parallel rays will get focused. In the case of a diverging lens, though, those parallel rays are only ever appearing to focus anyway, right? If we were to trace their path backwards, like we did with the other one, right? When we traced the path backwards from a focal point out, they all went parallel. And so it made sense that no image would be formed. However, that's not what's happening here. Let's just draw it and see. Okay, there's my object right at the focal length. Let's do our 2 rules and a check. Parallel hits the principal plane and then gets refracted in such a way that it is projected back through the primary focus. Okay, through the center, no refraction. And you'll notice, looks like an image is actually forming, right? Do our third check, directed towards the secondary focus, but once it hits the principal plane, gets refracted parallel to the principal axis. And then that ray gets projected back. By the way, folks, if you're uncomfortable with the fact that we're projecting these 2 rays back, but we're not projecting this ray back, go ahead and project it back. In fact, we kind of are, right? You can project it back if you want. Guess what? It's along the same line, right? So in a way, they are 3 projections. Okay. So again, bang on, dead, right there. Looks like an image is forming. It's a virtual image, it's erect, and it's diminished, like we should always get for a diverging lens, right? Doesn't matter if we're at the focal length or not, okay? Again, that has to do with the fact that a focal length is where parallel rays converge or appear to converge. So if they only appear to converge here, then we don't have that problem of all rays leaving are just going to go parallel, because parallel rays were never really converging here to begin with, right? They were only appearing to converge here. And so we do get an image forming here, even when our object is at the focal length. It's a virtual, erect, and diminished. So just before we wrap up this first kind of intro to diverging lenses, I'm just going to do this kind of applications page. So jumping ahead a bit in the notes, this is on page 42, okay? So just to look at this before I go into examples with the diverging lens, There's so many applications of this optics stuff. It's actually a great field to get into if you're wanting to work in physics. Tons of jobs in optics, okay? Um, so the basic idea, your eye has a lens in it, and it's a convex lens. It's a converging lens, okay? So what it does is it takes light rays from distant objects and it focuses it. It needs to focus it on your retina for your brain to do something with that information. It literally takes the rays, forms an image on your retina, and then that image gets sent to your brain and you say, okay, I'm seeing something. Now, problem is, some people's lenses are too weak, some people's lenses are too strong, some people's lenses can't adjust properly, okay? And so you have two major types. You have nearsightedness and you have farsightedness. So in nearsightedness, what happens is that parallel rays from a far object will converge too early, right? If the object's far enough away, then it's putting out rays. Well, the ones that are going to hit your eye come from far enough away that they essentially end up coming in parallel. And so you're nearsighted because these parallel rays, they come in, right? And they get focused too early. So how do you correct nearsightedness? You take a diverging lens. And what that does is it spreads them out a bit so that your over powerful lens, your lens that was focusing them too early, right? Your retina is back here. So they should be focusing here, okay? It spreads them out a bit so that now when your over powerful eyes lens converges them, it has to go a little bit farther. It has to work a little bit harder. And so that fixes the issue so that they now focus on your retina and now you can see again. Okay. So if you wear glasses and you know you're nearsighted, take them off your face right now and kind of look through them, right? What does everything look? It looks diminished. It looks upright, right? I'm doing it right now. I'm nearsighted. In fact, when I was testing out the diverging lens earlier with you guys, I kind of said, this is pretty close to my prescription. I can see really well with this little diverging lens, okay? So that's how that works. It spreads out these rays that are over here getting converged too early. Well, spread them out a bit. And then when they get converged, they'll get converged at the right place on your retina. So an image is formed. You can also think of this as, remember, how did we say the image was formed in terms of distance from the lens? The image formed by a diverging lens is it appears closer than it really is, right? So essentially, what your diverging lens is doing on your glasses is making an image of the object that's closer to you, right? You're nearsighted. You can see stuff that's close. Well, make an image of the object that's closer and your eye will be able to handle it. That's essentially what's happening. Okay? Taking this distance object and saying, well, let's pretend it's here. There's also farsightedness, where you can see stuff that's far away pretty well, but you can't see stuff that's too close to you, right? You are farsighted. You can see far stuff, but not close stuff. What's happening there? Well, stuff that's really close, right? As those rays leave, they actually are still, they're not quite, they don't have enough distance to get parallel. This is kind of a bad picture because it makes it look like they have a problem with the parallel rays. They have a problem with these diverging rays that you can see these are still hitting your eye and they're still kind of spread out. Now, in a farsighted person, your lens is not converging enough. It's too weak. It's not converging it early enough, okay? And so your retina is here, but the image is forming back here behind your retina. So that's no good. Your brain can't do anything with that, right? The image needs to form on the retina. So how do you fix that? Well, help your lens out, help it converge it a little bit easier. So take those diverging rays that are coming from this object, converge them a little bit before they even get to your lens, and then your lens can do the rest of the work so that by the time it gets to the retina, it's focused. Okay, that's how corrective glassware works. Pretty cool. Okay, microscope might not look like a microscope, but slap a tube on it and there you go, microscope. Okay, how does it work? You put an object there, you have a converging lens form a real image. Okay, important that it's real. If it was virtual, that would be it. You could form an image, but then you can't do anything more with that image because if it were virtual, there's no light rays to do anything with. Right? So we make a real image here using our converging lens. Notice the object is beyond the focal length, right? Remember from yesterday, that makes a real image with a converging lens. But we place another lens here and we place it so that the real image forms inside the focal length of this eyepiece lens, the one that your eye actually looks through. So now that real image, if we follow, you can see they're following our two rules here, right? They're going parallel through the focus point being on your eye, right? And through the center. They did the same thing here, parallel through the focus, and then just through the center, no refraction. And they took this real image and our eye would trace it back and see now a huge virtual image, right? So that's just what's happening there, okay? Telescopes, of course, are another good application of this stuff, okay? There's two main types of telescopes. There's refracting telescopes and reflecting telescopes. Reflecting telescopes, what do you think they use? Mirrors, right? So these are actually better. The reason is that when you're looking at something very distant, very far away, one of the main issues with seeing it is that there's not a lot of light hitting you from that thing, right? Think about a star that's billions and billions and billions of kilometers away. Not that much light is actually going to reach us from that. So we need to collect as much light as possible. With a lens, a little bit of light is kind of lost in that transmission. Not all of the light gets through. Some of it is reflected, right? Some of it is even absorbed, okay? A lot of it does get transmitted, but not all of it, right? So we lose a little bit of light here, but it's the same idea. So parallel, because a star is so far away, the rays are essentially parallel, are almost exactly parallel, right? They get converged a bit here, okay? And then they go through the eyepiece to our eye. Same idea as the microscope, pretty much there. With a reflecting telescope, so reflection is a much more efficient process than refraction. Yes, some does get absorbed, but for the most part, almost all light gets reflected, and then we focus it. We have a converging mirror here to focus it onto this mirror, which then converges it onto our eye and forms an image. Okay, so I'll stop the kind of intro to diverging lenses here. I'll make the other video now with going through these examples here, and also just some kind of wrap up examples that deal with both kinds of lenses and thinking about each. So if you want to see that as well, check out the example video. You can kind of skip around to the one you want to see, but I'll end this one here. If you're looking for practice at this stuff, you don't want to see the examples, you can go ahead and try the questions that are posted from the 13.4B assignment in the Google Classroom or in the agenda that go with this topic.